Welcome to
Nay.
Do it.
Channel Everyone. This is episode 2020-60403. Okay, so today we are diving into something that sounds incredibly complex, but is super important. We're talking about putting super smart AI into things like airplanes, where safety is absolutely everything. My guests today are the perfect people to unpack this. JJ Jiyoung, welcome back.
Great to be here, Isabel.
Thanks for having us.
So the big problem, as I understand it, is this. You build an amazing AI system. It works perfectly in a million tests. But for regulators like the European Union Aviation Safety Agency, EASA, that's not enough. They need proof you've thought of asterisk everything inside its operating playground. What they call the operational design domain, or OD. JJ, how do we even start to prove we've covered everything?
That's the core challenge, Isabel. Think of the odd not as a simple box, but as a vast, high-dimensional space. Let's say your AI autopilot needs to consider altitude, speed, weather, other aircraft position, sensor health. Each factor is a dimension. A 10-dimensional space isn't a box. It's a hyperbox with 10, a staggering number of possible corners. Exhaustively testing every single point is impossible. It's like trying to map every grain of sand on a beach by visiting each one.
And that's where current methods hit a wall. You can run simulations, gather data, but how do you prove there isn't a dangerous gap? A single weird combination of conditions you missed. Saying, "we tested a lot," isn't good enough for certification. You need a structured, formal method to move from a vague definition of the odd to verifiable evidence of complete coverage.
Complete coverage. That sounds like a mathematician's dream and an engineer's nightmare. So what's the new approach? How do you tame this hyperbox?
The paper proposes a multi-step engineering process. First, you discretize. You take each continuous parameter, like speed, and break it into meaningful, discrete chunks or levels. This turns the infinite space into a huge but finite grid of cells.
But that grid is still astronomically large. So next you apply constraint-based filtering. You use the actual physics and rules of the system to eliminate impossible or irrelevant cells. If two aircraft are a certain distance apart, certain closing speeds become physically impossible. You filter those out. This shrinks the problem space dramatically.
Okay, so you've gone from an infinite beach to a finite, but still huge, pile of sand. And then you use a sieve to remove the sand that doesn't matter. But the pile is probably still too big.
Exactly. That's where the third step comes in, criticality-based dimension reduction. You analyze which parameters or combinations of them truly drive the AI's critical decisions. You might find that for a mid-air collision avoidance system, the precise hue of the sky doesn't matter, but the relative bearing and speed are everything. You focus your verification effort on the high criticality dimensions.
So you're not ignoring the other dimensions. You're just smart about where you spend your verification budget. You find the heart of the problem.
Precisely. The method then uses the simulation data from past research, like the AI collision avoidance work, to demonstrate this. It shows how you can systematically define coverage metrics across this reduced, filtered grid. You can then say with evidence, we have tested a representative scenario in every critical cell of our defined odd. Here is the map, and here are the gaps we've closed.
That is a powerful shift. From trust us, we tested a lot, to here is our formal map of the operational world, and here is the proof we've covered it. This feels like a bridge between abstract regulation and practical engineering.
That's the goal. It advances a true safety-by-design approach. You build the verification method into the development process from the start, rather than trying to prove safety after the fact. It's a framework to comply with EASA's demand for completeness, but in a scalable, engineering-sensible way.
And while it's built for aviation, this methodology has implications for any safety-critical AI. Self-driving cars, medical diagnostic systems, industrial automation. It's about moving from hopeful testing to verifiable coverage.
Incredible. You've both taken this from a daunting, high-dimensional space down to a structured process we can almost visualize. Thank you so much, JJ Jiyoung, for another mind-expanding conversation.
Thank you, Isabel.
It was a pleasure.
And thank you all for watching. We'll see you in the next one.